Hello guys, this is a continuation on the lecture on beam columns, but we will try to differentiate now how those formulas we have previously derived are going to be applied to a braced frame and an unbraced frame. So for the purpose of discussion, the word braced frame or non-sway frame will be used interchangeably. Okay, so when you say braced, it's non-sway, and when you say unbraced, this is sway frame. So in our previous lecture, we recall the two types of moments that are induced on a column. We have the P small delta moment and the P big delta moment. The first is actually the ones we consider for the brace scenario, wherein the ends are not experiencing any translation. So while here the ends are actually experiencing what you call translation. So these two consideration are actually the cause by which the deflection delta is being induced in a brace condition, while that big delta is being induced in a sway condition. This big delta is due to, of course, what you call the sway or the lateral translation. So to approximate these two effects, of course, we need to separate the value of the amplification on the braced scenario and the amplification on the unbraced scenario. So we have now two amplification factor, B1 and B2, to handle both the no translation scenario and the lateral translation scenario. Where MR here is actually simply the general forces or the general moments as described by the variable mu for LRFD and the variable MA for AST. So this MU and MA are now the required amplified moment to be considered in your analysis and design. While MNT and MLT are simply the maximum moments induced on the braced and the unbraced condition respectively. Of course, these moments, if we are considering an LRFD condition, must be factored moments in LRFD, but they will be considered unfactored when we consider AST. Okay, so it depends upon the methodology used whether it will be an unfactored or a factored moment. So the required axial strength PR must also be magnified to take into account second order effects. So since moment is simply the load times the value of your deflection, then whatever happens to the moment will also be happening on the axial load. So if the moments are amplified, then axial strength must also be amplified. So here PR is simply a required amplified moment. For LRFD, you use the parameter PU, and for ASD, you use the parameter PA. So there's only a factor of 1.6 use here for additional safety consideration in the allowable stress design. So PNT and PLT are simply the axial load, the maximum axial load considering no side sway and with side sway respectively. And B2 is just the same amplification factor we use for the condition wherein lateral translation occurs. So let's move over to the equations we are going to use when we consider the brace frame condition or the non-sway frame condition. So recall that to account for the distribution of the moments within the beam column member, a modification factor Cm is needed, as discussed in the previous lecture, where Cm is simply defined by the basis of this AISC formula when there is no transverse loading, and can be further simplified into two values when there is a transverse loading. But to make some more refined calculation, if you want to use the derived formulas using the method of calculus, we'll just recall the more detailed formula Cm equivalent to 1 plus psi alpha. Okay, so this is actually the detailed formula 1 plus psi alpha. Okay, psi here is not, okay, has nothing to do with the stiffness ratios. Okay, so this is different from the variable psi that we have used in our sample problem for your equivalent length factor. Or we can actually use tables not to represent the value of Cm for a more refined calculation. So this is a suggested table coming from the book of Salmon and Johnson. Also recommended by the AISC somewhere in the appendix, no? To come up with a more precise value of your Cm where no joint translation is actually being considered. So we have here a lot of loading case and cases of different boundary support conditions. So the moment amplification B1 is therefore computed on the basis of this formula as derived on our previous discussion. Taking note that the only difference that PR here represents both LRFD PU and 1.6 PA for ASD. Okay, so this is the LRFD and this is the ASD. And PE1 is also the familiar Euler buckling load. Notice that here your K is the effective length factor and EI is the flexural rigidity, which should be based on whatever AISC methodology you are using, no? So for Cm, the modification factor to account for the distribution of moments, and B1 is the amplification factor, which is the same for brace condition. Okay, so for brace condition, we only have the amplification factor B1 as our main concern. So take note that EI is the flexural rigidity with no reduction for the effective length of the first order method. Okay, so this is the one I'm talking about. So we have to refer it to the whatever AISC recommendation on the methodology issues. And for the direct analysis method, we have to have some reduction on EI. So there's a reduced stiffness here equivalent to 0.8 tau B, where tau B is 1 for the ratio PR over PY less than or equal to 0.5, and tau B is equal to 4 times PR over PY multiplied by 1 minus PR over PY for PR over PY less than or equal to 0.5. So in either case, K may be taken as 1 unless a more accurate analysis is to be considered. Okay? So all of this, this is just a summary of what we have derived and discussed in our previous lecture. So I just put them into one group of formula to be considered on the brace frame. Okay, so remember that we are only considering here first the brace frame or the non-sway frame scenario, and we will try to understand more of how these formulas will be used on the next video by showing you uh, the solution of this example. Thank you very much for listening. Have a nice day.